and the physical science behind our understanding of climate change. And then we're going to talk about forests and the global carbon cycle. And then we'll get into a little bit of research, some of the research that's going on in my research group on the projected effects of climate change on tree growth, and really try to get at this question: can we use the past to predict the future? Yes, but there'll be some caveats and some ways in which we can do our work better that I'll talk about. And then I'll end by talking about a new research initiative that we've started working on as of last fall to jumpstart a North American Treering data network based in forest inventory plots to really keep track of how much what effect we're having on the carbon cycle. So let's go ahead and get started. And I'm going to pose a series of questions. And I see one student from my conservation biology class in here last year. And so she's going to recognize these questions because these are questions that I pose in a classroom setting. And you get the cheat sheet down there in the right-hand corner, the bottom corner. You get this visual to be able to try to figure out the answers to these questions. So, is our atmosphere heated from above by the sun, or is it heated from below by the earth?
Below.
Okay, now here's another question. The sun radiates, does it radiate ultraviolet and visible radiation? Or does the sun radiate infrared, which is long wavelength or lower energy radiation? And again, I'm giving you a little bit of a, let's see. Well, I'm giving you this graphic here to remind you of the electromagnetic spectrum and where the ultraviolet, the visible, and the infrared falls on that spectrum. So, and the Earth, does the Earth radiate ultraviolet and visible radiation, that is the short wavelength and high energy radiation, or does the Earth radiate infrared, which is long wavelength, lower energy radiation? All right, another question. Greenhouse gases, do they absorb ultraviolet or visible light or infrared radiation, which is radiated by which, the sun or the earth? And then these greenhouse gases re-radiate that energy in all directions, increasing the amount of heat retained in the Earth's atmosphere. And then finally, one last question here. One of the pieces of evidence for the greenhouse effect is that the troposphere, that is the part of the atmosphere from the Earth's surface to about 10 kilometers up, is that part of the atmosphere, is it warming or is it cooling? And then the stratosphere, in contrast, the stratosphere, that part of the atmosphere that is greater than 10 kilometers and going out into space, is that warming or cooling? So take a moment, talk to a neighbor, work on these questions, and you can use these visuals to figure out the answer to these questions. So I'll give you 2 minutes. I'm going to time this, and then we'll come back and come back to the answers. Feel like you got answers to these questions? Let's go through these one by one. All right, let's give this a try. So our atmosphere, is it heated from above by the sun, or is it heated from below by the earth?
Below.
I don't know if I want to call it you, Max. That's my son. Anybody else want to jump in?
Below.
Heated from above by the sun or heated from below by the earth? Okay. All right. You know what? I'm going to accept that answer. But now, so here's the way it's heated from below in the sense that, now if you think about putting a rock out on a warm June day, which is what we're about to start experiencing, right? A warm June day in Tucson, what happens to that rock?
Absorbs.
It gets hot.
Yeah.
Yes. And now, the Earth is essentially a giant rock in space, and space is a cold place. Now, if you put a rock in the sun, it warms up, and it warms up the things around it. It creates, this we know from experience, when you go outside on a June day and you put your hand up against a rock or a wall or the side of your house or something that has been absorbing heat, it re-radiates that heat. And so our atmosphere is being heated from below by the Earth being a giant rock in space, space being cold, but that giant rock being heated by the sun. So our atmosphere is being heated from below. Okay, so the sun, does it radiate UV, infrared, visible? Which of these parts of the electromagnetic spectrum? Okay, I heard UV. I heard all. Mostly the UV and visible part of the spectrum. And then the Earth. What is the Earth radiating? Is it radiating UV, visible, or infrared? Infrared. Yeah. I mean, you got that information here. Oh my goodness. I think the batteries might be dead on this.
Uh-oh.
Oh, it doesn't work on the screen?
Do it on the ground. Do it on the wall.
All right, well, I'll just use my finger. So the Earth does radiate infrared radiation, and that's heat coming off of this giant hot rock in space. Greenhouse gases, what do they absorb? Which part of the electromagnetic spectrum are they relatively transparent to, and which part of the electromagnetic spectrum do they absorb and then re-radiate? So UV, visible, infrared. Yeah, infrared. So that's the characteristic of greenhouse gases. Their defining characteristic is that they absorb infrared radiation. And here's a list of some of the examples of what some of those greenhouse gases are. Carbon dioxide, we're all familiar with. Methane, water vapor in the air. Nitrous oxide, ozone, and chlorofluorocarbons are all greenhouse gases. And then, so one of the pieces of the evidence for the greenhouse effect. So the troposphere, is that warming or cooling? Yes, and the stratosphere? Cooling, right. And so in this part of the picture, so some infrared radiation is trapped by gases. What does it mean by trapped by gases? It means that these molecules in this list absorb infrared radiation and then they re-radiate it in all directions. And some of that heat is going to go back to the surface of the Earth. And so we need these greenhouse gases to keep our planet from cooling off too much. But when we add more of these greenhouse gases to the atmosphere, we change the energy balance of the planet. How much heat is escaping to space, and how much is being bounced back to the planet and warming the planet. So when we add these greenhouse gases to the atmosphere, we change that energy balance. And that's the physical science basis behind climate change and global warming, and that physical science has been understood since the late 1800s. And scientists have been have pointed out that eventually, as we put these greenhouse gases into the atmosphere, it's going to cause warming. That's been pointed out by scientists since the 1950s, at least. Okay, so here's a report in 2013 about the global carbon cycle. Where are we? So this is the 5th assessment report of the IPCC, the Intergovernmental Panel on Climate Change. So let's take a look at some of the numbers that come directly out of this report. So between 1750 and 2011, that is beginning at the Industrial Revolution in 1750 up to 2011, 2 years before this report came out, we have added about 555 petagrams of carbon to the atmosphere. So a petagram is 10 to the 15th grams of carbon. And just to put this in a more human perspective, every mile that you and I drive in our cars is adding a pound of CO2 to the atmosphere. It's incredible. It's incredible. It blows me away. And in terms of parts per million, the composition of how much CO2 is in the atmosphere, we've gone from 278 parts per million in 1750 to what's the number today? Curious, anybody? Yes, you guys know the number, 400. And so that's an increase of about 44%. So we've increased the concentration of carbon dioxide in the atmosphere by 44%. That's incredible. We are a planetary force. We'll come back to this theme that we are geoengineers at the very end of the talk. But these are what the numbers look like in terms of how we are influencing the carbon cycle and how we are changing the atmosphere. And we know that this changes the energy balance and it's changing the climate system. Let's take a look at those numbers. So we had this number here, the 555 petagrams of carbon that we've put into the atmosphere since the beginning of the Industrial Revolution. Where has that come from and where is it going to? The sources, where is that coming from? And the sinks, where is that going to? So sources, about 2/3 of that 555 is coming from fossil fuels and burning of fossil fuels and other kinds of industry, making cement, for example. And then about 1/3 of it is coming from what we call land use or land cover change, so deforestation and other kinds of activities. Where is it going to? About half of it is staying in the atmosphere and increasing that concentration of CO2 and other greenhouse gases in the atmosphere. The other half is ending up in these two places. The ocean, the world's oceans, which is causing what problem? Ocean acidification. And the other is being sopped up by the world's terrestrial ecosystems, primarily, especially forests. So forests are doing this incredible ecosystem service for us by sequestering carbon. When they do photosynthesis, when plants do photosynthesis, they take CO2 out of the atmosphere and they turn it into sugars and they turn it into biomass. So trees are doing this for us. And so they have been acting, this is to emphasize this point, forests have been globally an important carbon sink, sequestering about 1/4 to 1/3 of those excess greenhouse gases, CO2, that we're putting in the atmosphere. The problem is there's a lot of uncertainty, honest to God, scientific uncertainty about whether these terrestrial ecosystems are going to continue to do this as temperatures continue to warm and CO2 concentrations continue to go up, or is that land sink, this carbon land sink. So here's 0, and here's time on this axis, and we've got the past, and then we've got the future. And we have a pretty good handle on the past. These would not be very good models if we didn't have a pretty good handle on the past. But look what happens as we move into the future. These models say different things about what's going to happen in the future. So we have this axis here is again petagrams of carbon per year, 10 to the 15th grams of carbon per year. We've got a positive sink, so taking carbon out of the atmosphere by 10 petagrams of carbon per year versus a source of 6 petagrams of carbon per year. So 16 petagrams of carbon per year of uncertainty about what is going to happen, how these terrestrial ecosystems are going to behave.
Those are different model projections?
Those are different models, yeah, different dynamic global vegetation models, yeah. So, will forests continue to be a carbon sink, or will they become a carbon source and a positive feedback to the climate system in the future? And when I say positive feedback, that sounds like a nice thing. But in this case, a positive feedback is not a good thing. So this is a nice quote from a scientist in New Mexico, Nate McDowell, and I think he captured this really nicely. So if forests are experiencing climate stress, drought stress, and they die, if those trees die, then they are no longer taking carbon out of the atmosphere. That means there's more carbon dioxide that's staying in the atmosphere, which causes more warming, which causes more drought stress to the trees, which causes more death of forests, which means less carbon taken out of the atmosphere. So it's a positive feedback in the sense that there's more forest mortality and more warming that feed each other. And so this is what we call a destabilizing feedback. Right now, forests are acting in a stabilizing manner. The question is, how much longer are they going to be a stabilizing feedback, and will they become a destabilizing feedback at some point? And the argument that I'm going to make tonight is that we can use tree rings to get a better handle on this scientific uncertainty and this question about, are forests going to continue to be a carbon sink? What are the thresholds or tipping points beyond which they may become a carbon source and a destabilizing feedback on the climate system? So now, if you've been to any of these series before, you've maybe seen some tree ring science by dendroclimatologists who reconstruct past climate using tree ring records. So we have a tree ring record that so this is, again, is a time axis. So the tree ring is sampled here, and then we have records that go backwards in time, maybe centuries, maybe millennia in the case of the bristlecone pines. Then we have the climate record, which is the instrumental record. Weather stations, rain gauges, temperature gauges. So we use the overlap between the two to build a statistical model of the relationship between climate and tree growth, where we predict variation in climate based on variation in ring widths. So we have just a really simple linear model here, a correlation or a linear regression model that predicts climate as a function of ring width variation. And that allows us to then reconstruct climate in the past. So similarly, dendroecologists can use this same kind of statistical relationship between variation in climate and variation in tree growth, variation in the width of these rings, to then take a projection about future climate, so these IPCC scenarios, and then predict the width of the rings as a function of future climate. So sort of reversing this equation and projecting future growth. So, and that's been done. This is the first paper that I'm aware of that did this, published in 2010, including Steve Levitt here in the Tree Ring Lab, and this was led by Park Williams, who was in the Tree Ring Lab at the time. Using data from the International Tree Ring Data Bank, here's the projection of the percent change in the ring width index across the continental US. You see brown colors are decline, or predicted decline in growth. Green colors are predicted increases in growth. You see really a nice is maybe not the right word, but a strong decline in the ring width index centered here in the Southwest. So where are we? This question: can we use tree rings can we use the past to predict the future? Can we use information from these tree rings to predict future tree growth? So one answer to this question is yes, but there's something that we know about the way that the sampling was done for this kind of dendroclimatology. So most of the data that are in the International Tree Ring Data Bank, that data bank that I mentioned in the previous slide, They were collected by dendroclimatologists who were interested in studying the climate system and reconstructing past climate. And if you're interested in studying the climate system, reconstructing past climate, then you really want the tree that is acting like the best thermometer, the best rain gauge, the most climate-sensitive trees on the landscape. And so they sample trees that look like this, that are on steep, rocky slopes, have little soil that has not very much soil-water capacity to buffer those trees against the kind of variation in drought stress from one year to the next. And the result being that you have this nice sort of variability in the width of the rings from one year to the next. So wide ring in one year, and then a narrow ring, and then a narrow ring, a narrow ring, a little bit wider, narrow, etc. So really a lot of variability from one year to the next. And that allows dendroclimatologists to pick up the climate signal and reconstruct, have a nice variability that allows them to reconstruct past climate. The kind of sampling that you want to do if you want to study a forest ecosystem is not the same kind of sampling. If you're interested in predicting how the forest ecosystem is going to behave in the future, you want a representative sample. And this is the very same principle as a representative democracy, right? So in a representative democracy, we want the people in Congress to look like us and be able to represent our experiences. And the experience of this tree is not the same as the experience of this tree. And if these trees are more numerous on the landscape than these trees, then we want more trees like this in our sample and fewer trees like this in our sample. So we want to have sampling that reflects what's out there on the landscape. If we want to predict how the forest as a whole is going to behave, we want a representative sample. And so about 4 years ago, I started collaborating with these guys, John Shaw and Justin DeRose, who are both with the US Forest Service. And they had discovered about 10 years ago a bunch of boxes in a storage room that were filled with increment cores that had been collected in forest inventory plots throughout the 8 interior western US states during inventories between the 1980s and the 1990s. And so it was about 20,000 increment cores that had been collected, brought in, mounted into the core mounts, and then put in boxes and forgotten about. And so they were rediscovered while there was moving from one room to another or one building to another. The guys who were doing the work brought up one of these boxes and said, hey, do you want us to throw these in the dumpster or do you want us to keep them? And so John Shaw had the foresight to say, do not throw those away. And ever since then, we've been working on processing these samples. In the last 4 years, so we've been collaborating in the Treering lab with Justin and John, and right, so this is sort of the latest numbers as of actually about a year ago. So about 18,000 cores measured in almost 10,000 forest inventory plots, and usually it's about 1 increment core per plot. So very, very different kind of sampling than the traditional dendroclimatology kind of sampling. So for the last 4 years, as I said, we've been working on processing the cores that were sampled in the state of Arizona. And so this shows you a map of sort of the big 3 species that we have the most of, the most samples of, and a list of the crew of undergraduates and also masters and a postdoc lab technician, people who have generated these data, including with some faculty seed support from the Institute of the Environment and the College of Science. So thank you very much to those funding sources. And this has been, a great research experience for each one of these students working in the lab. So what I want to show you is a comparison of the climate sensitivity of these 2 different kinds of samples. And so Here I've redrawn that classic figure of the kinds of trees that you would sample for dendroclimatology versus these kind of forest inventory, average Joe Schmo kind of tree in the forest. Giving you this sort of gradient of soil depth and soil moisture capacity. And what you see is that these trees that were sampled for dendroclimatology, they have higher variability from one year to the next in the width of the rings, which is what we expected, and the data really show that clearly. This is what the map of those two contrasting samples look like. So the forest inventory sample is really very evenly spread out over the landscape and sort of comprehensively sampled. And then what we did is we created a statistical model that predicts detrended ring width as a function of cool season precipitation and warm season maximum temperatures in the previous fall and then the early part of the current year growing season. And if you look at the regression slopes, so the slope of the line, the relationship between the width of the ring that you're predicting with climate data, the slopes are steeper for the dendroclimatology samples, these trees that we expected to be more climate sensitive. They are indeed more climate sensitive. So on average, the climate sensitivity of these dendroclimatology or ITRDB samples is about 50% greater than the FIA samples. And so this is what the values look like, the regression slopes, the steepness of the slopes. It's steeper when you look at these dendroclimatology samples. So what does that mean when you forecast future growth of these trees? So this is work led by Stefan Klesse, a postdoc in my lab, who actually is no longer in my lab, moved on to his next position. This paper just came out last December, and the red line shows you, this is the historical record, so this is the past up to the present, and then we have future projections of ring width index, or relative growth of the trees. And what you see is that the red symbols, so from the forest inventory data, they're higher than the black. So the black are those dendroclimatology, those most climate sensitive trees. So the predicted decline, the decline that's predicted based on the forest inventory samples, is 29% less compared to the samples that are taken from those most climate sensitive trees. So this might be a bit of a Rorschach test. If you're an optimist or a pessimist, this is either a glass half full or a glass half empty. You get to decide. We're not predicting that tree growth is going to increase. This is still a decline that we're predicting, but there's less of a decline based on this forest inventory, this representative and unbiased forest inventory sample. So in other words, it's an upwards correction of the predicted decline of forest growth based on the forest inventory data. Okay, so can we use tree ring data to project future tree growth? Yes, but we want to do that with a representative data set. We want to do that with a data set that really represents what the trees look like out on the landscape, and not the really special climate sensitive trees. But wait, there's a problem. The future doesn't look like the past. So if the future doesn't look like the past, how can we use the past to predict the future? So this is what I showed you at the beginning, was this idea that we're just going to fit a linear regression, and then we're going to say, okay, if temperature warms, then we're going to move up this direction on this line, and then growth is going to increase. The problem is that at some point, one would think maybe further increases in growth might not be a good thing for these trees, and they might actually become a bad thing. And this is sort of our conceptual model, just based on a basic understanding of the forest biome, the climatic conditions across which we see trees. So in cold places, trees tend to have a positive response to warm temperatures. They might be limited by temperature. These might be high latitude in Canada or Siberia. These are trees that will respond positively to warmer temperatures and a warmer than average spring. So maybe somewhere in the middle of the forest biome, the actual absolute growth is higher because these are not climate stressed trees, and they might not be particularly sensitive to variation in climate. And then maybe somewhere at a higher end of the temperature spectrum, in a warmer place, for example, here in the Southwest, in our Sky Island mountains, in the Catalinas and the Rincons and these other places, there's a negative effect of warmer than average temperatures lead to a smaller than average ring. So this is a conceptual model. If that's the case, then using a simple linear, just a line to project into the future might give us a poor estimate of how these trees are going to behave in the future. So the solution to this problem is to use, one of the few solutions that we have is to use a space for time substitution. So the idea being that the behavior of this tree in the future is going to be similar to the behavior of a tree currently that occupies a different place, a place that's warmer. So this tree in the future is going to behave like a tree in a warmer place today. Does that make sense? Space for time substitution. I can only imagine that you're already starting to think what might be the limitations of this. There might be some problems with this, right? But we're going to go with this for now. This is our next sort of round of improvement. So the species that we chose to try this out, this space for time substitution approach, is this species, Douglas fir, Pseudotsuga menziesii. Will you repeat after me? Pseudotsuga. Pseudotsuga.
Pseudotsuga.
Menziesii. All right. I have to tell you, this was the very first Latin name that I ever learned. I grew up in Oregon, so if you grow up in Western Oregon, you grow up surrounded by Pseudotsuga menziesii. There's something about it rolls off the tongue in a really nice way. All right, so this species is amazing. It has this incredibly large geographic distribution. And this map doesn't actually cover the entire distribution. So it goes from 55 degrees north in Canada to 17 degrees north down in the state of Oaxaca in Mexico, which is not shown in this map. So that is 38 degrees of latitude. That's an incredible geographic distribution. For those of you who know a little bit more about Douglas fir, you know that there's a coastal variety and an interior variety, variety menziesii and variety glauca. So the coastal variety is really just up along the coast here, and then all the rest of this is the interior variety of Douglas fir. And if you've ever been to the Olympic rainforest, temperate rainforest, Olympic National Park, the trees are enormous. And here's another nice picture that I found on the interweb. Here's a guy measuring the diameter of a Douglas fir tree. It's an enormous, enormous tree. And then we also have Douglas fir down here in the Southwest. It looks like this photo was taken in Bryce Canyon. I stole this off the internet. The trees down in the Southwest, they don't get quite as big as they do up in the Olympic National Park, right? So an enormous amount of variation across this geographic distribution in mean annual temperature from just below freezing to almost 20 degrees average mean annual temperature. And then in terms of variation in mean annual precipitation across this distribution, an order of magnitude from 300 millimeters to 4,800 millimeters per year. So it's a great opportunity to use this space for time approach to predicting future growth. It also happens to be an incredibly important species commercially in the Pacific Northwest. There's a lot of commercial forestry based on Douglas fir forests. So again, this work was led by Stefan Klesse, a postdoc in my lab, and he compiled together what ended up being just a little bit more than 30,000 tree ring time series for this species, and that ends up being a little bit more than 2.6 million actual ring widths, data points to work with. This is the map of, so you can see how far south this goes. So some of that is from the ITRDB, some of it is from that forest inventory data that we talked about, and then another big chunk of the data comes from researchers, some of them listed here, but also many others who contributed data, were kind and generous enough to contribute their data to this project. So here's a conceptual model of what this statistical model is going to try to capture. So instead of just having a single line, every single tree ring time series gets its own line. It gets its own intercept and its own slope. Let's see here, I'll do this. And the idea here is that, so on this axis is mean annual precipitation. So in a place like the Pacific Northwest, the Olympic National Park, and Olympic rainforest, we've got these really large trees, so the average radial increment is high, and the sensitivity to variation in precipitation is they don't change, the width of the rings doesn't change very much. Kind of like train tracks, they just keep chugging forward. Down here in the Southwest then, we have less annual precipitation and we have lower productivity, so the width of these rings is smaller and their sensitivity to variation is greater. So that's sort of the conceptual model. And here's where I just need to take a moment to pay my respects and really pay homage to Hal Fritz. I won't spend a lot of time elaborating on this, but the figure on the left and the figure on the right are mirror images of each other. And so this statistical model that we built was published a long time ago in 1966 by Hal Fritz in the journal Science. This understanding that as you go to drier places, to the semi-arid forest border, the average ring width goes down and the sensitivity to climate goes up. And so he captured that idea many decades ago, and now we're just trying to capture that in a statistical model that's flexible. And I just wanted to mention that Hal passed away just a little bit earlier this year, and so this is my homage to the conceptual foundation that he laid for the work that I'm showing you. Okay, so what does it look like? What do the projections from this statistical model look like? And I'm going to show you, again, something similar to the result that you saw earlier, that if you use all the tree ring data, so the colors here this is predicted decline in the width of the ring, and then blue and purple colors are predicted increases. If we use all the tree ring data, which actually most of those end up being from the ITRDB and these other kinds of sampling schemes that target these more climate-sensitive trees, you get stronger predictions of decline. Whereas if you limit the analysis to just the tree rings from the forest inventory plots, again, you get less of a decline from those data. So mirroring that result that you saw before. So to summarize what we have so far, can we use tree ring data? Can we use the past to predict the future? Yes, we want to do that carefully. We want to do it with a representative data set. But no, gosh, we have to be careful about this because the future doesn't look like the past. Okay, well, yes, all right, maybe we can do this if we use a space for time substitution. If we had a little bit more time, I would love to actually hear your thoughts, and maybe in the question and answer session, you can ask me, maybe there are things that are coming to your mind about some of the limitations of this space for time substitution approach. In the time that we have left, I just want to tell you finally about a sort of a new research initiative that we're working on. And I want to put that in context. So where are we now on this planet at this point in time? So the Intergovernmental Panel on Climate Change, the IPCC, put out a special report last October, the Special Report 1.5. And the goal of this report was to evaluate what are the consequences of 1.5 degree of warming as opposed to 2 degrees. At the Paris Climate Accord, the countries agreed to limit the warming to 2.0, 2 degrees warming. So this report evaluates what are the consequences of 2.0 compared to 1.0 of warming. We're already at 1 degree of warming, And what this report showed us is that we're expected to reach this 1.5 degree of warming sometime between 2030 and 2052. So we don't have a lot of time. We have just a few decades to really change course about how we're influencing the composition of the atmosphere, the energy balance of the planet, and the ways that we're changing the climate system. And limiting global warming to 1.5 degrees Celsius is going to require not just making this enormous transition to net zero CO2 greenhouse gas emissions, but actually net negative emissions. That is a pretty alarming and profound sort of realization to swallow. 1 month later, in November of last year, the fourth National Climate Assessment came out. I don't want to spend a lot of time on this, but I just took this one sentence, copied it directly out of the National Climate Assessment. So without substantial and sustained mitigation and adaptation efforts, climate change is expected to cause growing losses to American infrastructure and property and impede the rate of economic growth over this century. So it's going to cost us a lot. The damage, we've seen this with the intense storms, hurricanes, Hurricane Harvey, flooding. These extreme events are increasing in frequency, and that's exactly what the climatologists have told us what is going to happen. Is going to happen with these changes in the climate system. And it's going to cost us a lot of money. So solutions. Also came out last fall in October of last year. I think didn't get quite as much press as these two. There was a report put out by the National Academies of Sciences. The title of it was Negative Emissions Technologies and Reliable Sequestration, a Research Agenda. So if we're going to need to do this, if we're going to need to do net negative emissions, how are we going to do it? And the National Academy's authors of this report said we've got 4 land-based negative emission technologies that are ready for large-scale deployment at costs that are competitive with emissions mitigation strategies, including reforestation, changes in forest management, changes in agricultural practices that enhance soil carbon storage. I didn't put the 4th one up here, I was running out of space. But what might be obvious here is that what I'm trying to emphasize here is that we can use forests. We can use these terrestrial ecosystems. We can manipulate them and manage them so that they can actually achieve this kind of net negative emissions. That's probably going to be an important part of our portfolio, our diverse set of strategies to change course in terms of the carbon cycle, how we're affecting the carbon cycle and how we're affecting the climate system. Okay, and so with that in mind, with that context in mind, we need an ecological monitoring network that can allow us to take really account for how much carbon is being sequestered by these terrestrial ecosystems. Verifying all of these countries, they made promises about ways that they're going to achieve net zero or even net negative carbon emissions. If they made that promise by saying we're going to do some afforestation or we're going to manage our forests to store more carbon, who's going to verify that? Who's going to prove that that's actually being done? And then also, improved forecasting, this uncertainty that we have about how forest ecosystems are going to respond. So the need is for an ecological monitoring network, and we think in the Treering lab, and I'm going to credit David Frank, actually was the one to initiate the idea for this idea of a national forest inventory-based tree-ring network that would be continent-wide across Canada, the United States, and Mexico. So to augment these existing national forest inventory programs that we have by adding sampling of tree rings. And so we got together last October, this group of people across these 3 different countries, here in the Treering lab to jumpstart and initiate, organize this idea of building this ecological monitoring network within the forest inventory, this National Forest Inventory programs, using tree rings to really count, sort of like counting our calories or counting our carbon budget. We need to know how much carbon these trees are sequestering. And the Canadians, as usual, are ahead of us. So there's a couple of maps for showing the tree ring data that they've already got going in their forest inventory plots. I showed you the work that we have and the data that we have in the western US. But just in Quebec alone, they have this collection of about 300,000 increment cores that were collected in their forest inventory plots. So as usual, the Canadians are ahead of us. We're doing our best to try to catch up and coordinate across these three countries. So just to wrap up, the message that I would like to get across and really close with, this may seem daunting, this idea that we need to manage the global carbon cycle, but I actually think it's sort of appropriate to bring this message to a garden, right? Because gardening is really on a very small scale that same sort of geoengineering. We move dirt around, we add carbon to the soil for our vegetable garden. Anybody who's done any vegetable gardening in Tucson knows you have to add a lot of humus, a lot of soil carbon to increase the fertility of the soil and the water holding capacity. There are all these things that we do. We've been planting trees in some places. We've been using fire to favor grasslands over forests and the wildlife that's associated with grasslands. This is a picture of the terra preta soils in the Amazon basin, which are these soils that have an enormous amount of carbon stored in them, very fertile soils that were created by Native Americans over the course of thousands of years of occupation and use in agriculture. And so we've always been doing this. We've always been affecting land cover, grassland versus forest, the amount of carbon in soils. We plant trees where we want them. We have already been doing this. We just need to be a little bit more organized about it, a little bit more conscious about what the effects are of our geoengineering. We've changed the composition of the atmosphere, and now we need to change some of our other behaviors to backtrack on that, so that we don't leave our children a mess to clean up. So Max is my son here in the front row, and I just wanted to say, Max, I sometimes pick up your dirty socks and your underwear at the end of the day, but
you don't tell them.
we parents, this generation is leaving actually a much, much bigger mess for you to clean up. So we need to clean up our act as adults and really start to think about the future and what we're handing down to the next generation. So with that, this is just a small selection of the many people that I have to thank for their support and their collaboration, their ideas, the scientific discussions, and lots of work. And with that, I want to thank you very much.